All right, let's check out this linear programming problem. And actually, we're going to quickly hop over to Geogebra to do this completely. But uh, let's first look at what we are doing and why we want to hop over and use technology. Okay. An objective function, one scenario is maybe, so first off, let me back up. This is the objective function, okay, the z part. You are not graphing that. Um, that would, require actually three dimensions, and some linear programmings actually will have three variables and would not be feasible or even possible to graph to solve these. Okay, there are other matrix methods for more complex problems, but for this video, we have x and y. We can, in fact, graph these and solve them. But the objective function is what we are trying to optimize, whether it be a max or a min. Okay, maybe this represents like a sales problem where you're making $5 off of the sell of whatever this product X is and $2 per product of whatever Y is. And then you have some constraints, whatever the word problem may arise to, these are the constraints. Now, it can be shown that the optimal points based on constraints will always occur on a corner. Okay, it's called the corner point theorem. We won't get into a proof of why, but typically I can't think of when we would not be in quadrant one, but typically we're going to stick with quadrant one because our x and y are positive values. I'm not saying there isn't a problem out there that wouldn't be constrained to quadrant one, but typically they are. Okay, I can't think of a scenario when they're not. And in order to graph all these, right, we first needed them in the form y equals mx plus b, or do the intercept method, and then we have to think which way it's shaded, right? It could be a less than or equal, or greater than or equal, and it gets messy. Okay, you would need graph paper or technology to get these precise, I suppose. Or we go back down and use a system of equations to actually find their intersections, right? Because we're going to have a bunch of lines. I'm going to completely rough sketch. I have no idea, like off the top of my head, what that really looks like. So suppose one does this, another does that, that I could see these two actually, maybe one is this and another is this. And then you have to shade and it gets messy. Maybe it was this region here, but we need these intersections. Okay, forget that mess. Let's hop to GeoGebra. Remember, geogebra.org is the website if you don't prefer to download. I think it's a great tool and worth downloading. So we're not going to enter the objective function yet, but let's enter the other, all the constraints for x minus y less than or equal to 16. I wanted to, at first I had this all typed up and I was just going to jump to it, but I wanted to show you the cool tools um, that we could graph and shade instantaneously like that. So it's pretty neat. Okay, there's the first constraint, 2x plus y is greater or equal to 11. Okay, and then what else is cool with GeoGebra? Your graphing calculator, TI won't allow these. Well, you can manipulate them, but you can't just type. For one, we have to solve y equals mx plus b, right? Then you have to tell it which way to shade. You cannot type an x equals 3 and shade that. And in GeoGebra, I didn't even need to solve. I could just enter them exactly how they're written. Love it. Okay, technology, free technology is even better. Okay, well, the view isn't the greatest, so let's just move this. All right, so the bounds. I don't know what all these little dots down here are. That's weird. But I don't know how to delete it on the iPad. That's okay. Ignore those dots. They must be there from something previous. All right. So I can see the region if I zoom in right here where it's shaded completely, right? It's this quadrilateral type looking figure there. But the problem I was having is if I use intersect and I select these two lines, okay, it's not doing anything. But if I go here, go back to my algebra, it looks like it is doing it, but it's not showing up. Okay, I don't like that. I don't know what is going on, but I found a workaround. I just want to show you it was in fact trying. Okay, my guess is that what was happening is we're shading, right, which means we're talking about an infinite amount of points here. So the intersection is actually too complex, not just a point. That is my assumption of what's happening, but I didn't feel like looking into it. So let's cheat. Type the same thing, but instead of using inequality, just use an equal. 4x minus y equals 16, enter. 2x plus y, that's cut off, what was it, equals 11. Okay, x equals 3. And y equals 8. Okay, remove the inequality, change it to an equal, and now what we do is like, it's still important to keep that inequalities, right? Because then I know the shaded region. But let's hide them because I know where I'm looking. And now let's go to intersect. Okay, I needed that intersection A. I needed that intersection B. I needed that intersection C. And that intersection D. Right? That is where that region was bounded. Those are the corner points. And I could, again, verify if I want to make sure. Yep, that was the region that is the darkest in Geogebra. By the way, there are a ton of options too. You could change the shading colors and everything about this. Geogebra is so cool. Up in that upper right, that gear, change the settings. All right, now I have these points. Well, I could go back and plug 3, 5, and 3, 8, and 6, 8, and 4.5, 2, okay, into my objective function, right? Z equals 5x plus 2y, and then use my point A, plug in my xy, see what value I get. Use B, see what value I get. Use C, see what, but let's utilize technology. Okay, that is one option. I don't even remember the points. But, you know, like we had, what, 3, 5, and 3, 8. So we can do that. For A, we would have 3, 5. So 5 times 3 plus 2 times 5. 5 times 3 plus 2 times 8 was B, right? We had the point 3, 8 and 3, 5. We could compare those. We'd get 25. We'd get 15 and 16, so 31. So far, I know B is the max. Okay, but we still have C and D. Nope, I'm using GeoGebra. Here's the tricky part. The more you have on here, the more letters GeoGebra begins to assign, right? A, B, C, D, equation 1, equation 2, equation 3, F, and then the points, capital A, B, C, D. That's geometry. They usually use capitals for points. So you have to pick a variable that has not been used. Normally we write function notation with an F, but F was used. F is y equals 8. So again, this is the trickiest part if you want to continue using GeoGebra, I need a G, because F was used, or H, or any other letter, okay? And we do X comma Y. Why is that? Because our objective function has X and Y in it, right? It introduces a third variable, Z. We could actually do Z of X, Y. I mean, it doesn't matter. Any new letter, G of X, Y equals, it was 5X plus 2Y. That is my objective function, right? Enter. Now, here's the cool part. Just do G. Oopsie. I was hitting answer. Okay. G, parentheses. So notice it called up the G function, right? 5X plus 2Y. But I want it to use A, G of A. Hit enter. 25. Let's verify. Is that what we got? Yep, 25, right? Oops. So go back to GeoGebra. It's working correctly. Could expand this because we're kind of done with the graph. It didn't stay. So test them all. G. It's kind of tedious typing this on the iPad. The computer is way easier. But we got 31, which we knew. G of C. 46. And G of D, our last point. 26.5. So the max was C. The max was the 6/8. Okay, that point up to the right. So how do we finish answering it? Whoop. So the max value is, what did we get? Sorry, 46 at the point 6/8. Okay, the max value is the actual value you get when you plug it in, 46 at the point 6/8, or you say when x equals 6 and y equals 8. Okay, that was the corner point that gave us the max value. So cool. Man, GeoGebra is awesome. And flip it back one more time. If you want to picture the shading on your own, right, you can eliminate some steps, get those equations, find the corner points, and create your objective function and do it that way. But I think tying it all together, it's pretty awesome. We could do everything at once.